So we're going to talk about tangent and normal vectors to sort of curves of vector functions, which we learned how to write as some R of t. And before we jump into the calculation, I'm going to draw a couple pictures so that we can kind of be on the same page about what we're looking for here. So maybe you remember, that's a line kind of. Go ahead and draw it like it's a 3-space thing, but for now you can just kind of think about this the same way you would have thought about these ideas in your prior calculus classes. So let's say this is your R of t. Then you should recall something like derivatives give tangent lines. So for example, if you're right here on this curve R of t, then if you take its derivative, it would be something like that, pointing off that way. Or ignore that I put these little vector symbols here. If this had been your, quote, y of x, then you would sketch this little tangent line to the curve anywhere you go that tells you y prime of x is kind of what you would have learned. And then sort of something new for us is going to be that what we're going to call normal vectors are second derivatives. And so we're going to have something that's normal to our tangent line is actually going to be obtained by taking 2 derivatives of our original curve. And so sort of, if you want a rule of thumb for what's happening here, it's going to be that our tangent lines are going to point, we'll write it down here. Our tangent vectors point along R of t. And then the word for what I said normal is going to be principal unit normal vectors. But just remember that this word is kind of normal. It's perpendicular to our tangent vector or line. Those are going to kind of point in the direction that your position is changing. And we'll give special names to all these things when we learn how to calculate them. But another way to kind of think about this is going to be sort of imagine like you're holding an object on a string and you're spinning it in a circle around you. So its path in that circle around you is going to be given by that R of t that forms, oh gosh, that big old circle, you know, just going to keep swinging round and round in a circle. And then, actually, oops, I want to put that somewhere else. That way I can have lots of room to write. So there's our R of t is this path that goes around a circle if you have this object attached to a string. We learned in section 9.1 nope, in section 10.2, that the derivative of position should be like your velocity. We actually did that in reverse. The integral of your velocity will give you your position. And so actually, let's go ahead and do it with a different color. So here's kind of it's a bad different color. That's the current speed your ball has. If it suddenly got disconnected from the string, it would go flying off in that direction. And you could consider that your velocity, and you would compute that using your derivative of position. Now, the part that's going to take a little bit of convincing for you is that if you take one more derivative, actually, I don't need that. Oh, red-green is bad color combination for people. Let's do red-orange, I guess. If you take one more derivative of position, we know that that should give your acceleration vector, just based on rules of position derivatives that are familiar to you. But think about it this way. You know that acceleration and force are related. The force you're applying to this object is you're pulling it in towards you. So this is exactly the direction you'd expect it to go. And it's going to be normal to your velocity vector. So hopefully that builds intuition for why R prime, and R double prime should be traveling along a curve, tangent to a curve, and perpendicular to a curve. Now I'm going to give you the formulas you need to work with these things, sort of like when you're doing your web work and stuff. So let's give ourselves some definitions. The baseline we're going to start from is we're thinking about R of t, a vector function. Again, that's just some curve we can draw in 3 space where we travel along it as t develops. This picture right here, start at some point, keep going forward. So for R of t, a vector function, the tangent to that function is, we'll call it, lowercase t is bad. So we'll just say the tangent is given by R prime of t. The unit tangent is going to be denoted by big T. And all you do is you take what we know the tangent vector should be, a derivative, and then you do what we say gives you unit vectors. You divide by the length or magnitude. So unit is just, remember how we created unit vectors in chapter 9. We've taken what we know a tangent should be and just made it length 1 by dividing by the magnitude of that tangent direction. So this picture I drew is what way R prime of t goes, and the unit tangent is going to be, just take something very small length right there, length 1. And then once you have that, you can go ahead and compute the, quote, principal unit normal vector. That's going to be denoted by capital N of t. And for that, you just take the t you had before, you take its derivative. So you take the derivative of something that was the derivative of r, that means it's going to be r double prime. That means it's related to this acceleration vector. This thing we said should be perpendicular to our tangent vector. And then because it's a because it's a unit vector, we're again going to just divide by that magnitude. And you're just going to want to remember these two formulas when you're asked about it. But you should remember what these things really mean. You're just looking at position. Tangent is basically velocity, one derivative. Normal vector is basically acceleration, two derivatives. And that's going to be the most intuitive way to remember how these formulas actually work. And then at the end, you're just taking out the magnitude. So I'm going to write this. Maybe it'll be helpful for you to know that that's just sort of like the second derivative of r, where we've normalized it by length. And then you normalize it again. So instead of that complicated formula, which I do not want you to commit to memory, I'm just going to say this is kind of like r double prime of t. Points in the same direction as r double prime, just scaled out by lengths. T points in the same direction as r prime, just scaled out by length.